Hello, I'm Cameron Kergaye, Director of UDOT's Research and Innovation Division, and it's my pleasure to welcome you to our 2022 Research Workshop, commonly known as UTRAC. This is a gathering of transportation professionals for the purpose of determining our research program. This workshop has been in its current format for nearly 30 years, and it's the primary way that we select transportation research projects and allocate our research funds. Every DOT across the nation gets special federal funding dedicated and preserved only for research, and it's a way that supports research without those funds being in competition for construction or other types of projects. It's a small bucket of funds, but programs like what we run here at UDOT are able to maximize the benefits by working with our research community to get their best ideas to help broaden and diversify some of the research that we are able to conduct. This year, there will be about 150 participants, similar to last year, about half from UDOT and half from our academic and research community. Most of this year's 62 problem statements are written by our academic and consultant partners with input from my DOT colleagues. All of the problem statements are submitted by someone at UDOT, a champion of the research. This is a format that has worked well for many years. And in the last couple of years, we conducted our workshop virtually, and we will do that, of course, again. One new aspect is we've asked for pre-recorded videos describing the problem statements and the proposed research. And we did that so that we can be a little bit more efficient while we meet virtually. It also gives UDOT more time to consider the problem statements and to formulate questions that we will ask when we finally do meet virtually. And I want to appreciate all the efforts from my colleagues at UDOT and our research community partners. It takes a lot of effort to think about what could benefit UDOT, what solutions could be brought forward. And I'm looking forward to engaging with everyone during this event. Later this year, we will put on our website some dashboard information about the metrics in our research projects. I think you'll find that interesting and helpful to know about all of our research projects, when we're completing them, and when you can look forward to the results of some of the research. Lastly, I would like to acknowledge this year's Trailblazer Award recipient. This is somebody that has put in numerous years to either conduct research or champion the implementation of that research. And this year, the award goes to Dr. Grant Schultz, a professor in the Department of Civil and Construction Engineering at Brigham Young University. He holds a Bachelor of Science and Master of Science degree in Civil Engineering from BYU and a PhD in Civil Engineering from Texas A&M University. Prior to his time at BYU, he spent 3 years at Texas A&M Transportation Institute and 7 years as a consultant in Utah and Idaho. He is a registered professional engineer in the state of Utah and is a professional traffic operations engineer. Dr. Schultz teaches courses in traffic engineering, transportation site planning, and global leadership, and he has taught study abroad courses in China and Europe. He also performs research in the areas of traffic operations, traffic safety, incident management, connected vehicle technologies, and access management. Dr. Schultz is the past chair of the ITE Transportation Education Council, and he is the current chair of the TRB Standing Committee on Access Management. It's my honor to present this award to you, Grant Schultz.
Hello, my name is Grant Schultz. I'm a professor in the Department of Civil and Construction Engineering at Brigham Young University. I'm honored to accept this Trailblazer Award and am privileged to have the opportunity to share this award with the many previous award recipients. Several of these individuals are ones that I have worked with or worked for, or have just been blessed to have been able to know and continue to know throughout the research that I've been able to accomplish. Today, I'd like to spend just a few minutes highlighting some of the things that I have done in my 18 years here at BYU. I'll also provide you with some information on one of my first projects that I completed, and then one of my biggest projects, and then most importantly, finish off by thanking all of those who have made this possible for me. I began working at BYU in January of 2004. Since that time, I've completed over $3 million in UDOT research funding for 20 different project champions. This work has led to the publishing of 45 UDOT reports, 28 peer-reviewed journal articles, and 46 peer-reviewed conference proceedings. This work has also led to the completion of 26 theses, with 4 more in progress, and 8 master's projects, with 1 in progress. In total, I've mentored 76 research assistants and presented my findings at 79 international and national venues, as well as 62 local and regional venues. I'm extremely grateful for the opportunities that UDOT has provided me to be able to move forward in my career. Some of the very first projects that I completed were done in 2006. And these included a variety of topics, including the economic impacts of transportation and evaluation of the advanced warning signals along Bangalore Highway, assessing the safety benefits of access management, and evaluating way and motion data in Utah. I don't have time to talk about all of these projects, but I would like to spend a couple of minutes talking about the evaluation of effectiveness of blank-out overhead dynamic advanced warning signal systems, or BODAS. The purpose of this research was to evaluate both the dilemma zone and the decision zone. This was accomplished by looking at different design assumptions and signal timing, as well as options for advanced detection and advanced warning. In our literature review, we identified several different methods for advanced warning signs. These included primarily sign-mounted dynamic signs with flashers. But UDOT wanted to do something more, so we looked at blank-out overhead dynamic signs with flashers. The study site that we did our analysis on was the intersection of 134 South and Bangalore Highway. This research was conducted back in 2004 and 2005. As you can see from these pictures taken at that time, there have been a lot of changes to this area since the research was conducted. To analyze the speeds in advance of the signal at 134 South, we used Wavetronics digital wave radar technology. At the time, Wavetronics was still developing much of their radar technology. In fact, this project was used by Wavetronics for the development of their smart sensor advanced technology. We used the radar to collect speed data in 7 zones in advance of the signal. The radar detector was located on the back of the advanced warning signal, and the signal controller cabinet was equipped with a laptop computer and support equipment needed to be able to collect the data at the zone specified. One of the key indicators that we used to evaluate the advanced warning signal were the results of the speed distribution at the intersection. We collected cumulative speed plots, developed box plots of speed data, and then generated probability grids of the speed results. The cumulative speed plot showed that prior to the installation of the advanced warning signals, the cumulative speed distributions were relatively constant at the 100-foot detection zone, regardless of the time before red. After the advanced warning signals were installed, the cumulative speed distribution plots showed very different results, especially for those vehicles 0, 3, and 6 seconds before the red. These drivers have been warned to prepare to stop, and the results showed that they did so. The general conclusions from the research showed that the advanced warning signal system did, in fact, impact motorist behavior. It also showed that when the signal was not operating correctly, motorists did not respond as expected. Minor changes were made to the lead flash time to find the sweet spot for the system design that we further developed in a follow-up research study. These systems have been installed along Bangalore Highway and in many other locations across the state, now with a static sign primarily for maintenance reasons. My largest continuous project came about as a result of the need to improve roadway safety at intersections on roadway segments in Utah. The purpose of this ongoing research has been to develop hotspot identification and analysis tools for UDOT to aid in their safety efforts. Over the course of the last 12 years, we've developed a series of models to aid in hotspot identification and analysis across the state. Today, I'll briefly introduce the most recent of these models, the crash analysis methodology for segments, or CAMS, and the intersection safety analysis methodology, ISAM. The foundation of the CAMS model was the roadway safety analysis method, or the RSAM. 2 statistical models were initially applied to the RSAM. These include the UTOT crash prediction model and the UTOT crash severity model. Both models were developed at BYU for UDOT and are formed from homogeneous segmentation of the roadway based on ADT, functional class, number of lanes, speed limit, and urban code. The intersection safety analysis methodology, or ISAM, is the second model in the suite. While CAMS focuses on roadway segments, ISAM identifies intersection crash hotspots. These were originally based only on intersections with 2 or more state routes, but then we have continued to develop the model and expanded to a larger set of intersections. Again, 2 statistical models are applied to the intersections, and these models, however, are focused on intersection-specific crashes. The current CAMS model uses 4 years of data to build the model and 1 year to compare against the distribution to determine hotspots. Crashes are ranked according to their percentiles, where the percentiles determined based on the predicted crashes as compared to the distribution developed from a hierarchical Bayesian model. We're currently working on a modification of the model so that more than 1 year is used to determine the hotspots. Upon completion of the application of the model, the results of the analysis are reported in an Excel spreadsheet and then mapped using GIS to help visualize the location of the hotspot segments. These maps show the result of both the CAMS prediction model results and the CAMS severity model results. Note that if a segment shows up on both models, it means there are more crashes than predicted, and more of those are severe crashes than predicted. The last step in the process is the creation of segment safety analysis reports. These reports are also shared with the traffic and safety engineers to help them quickly evaluate the hotspots identified from the models. There are numerous other steps involved in the CAMS and ISAM models. However, I will not provide that information today. I will note that the CAMS provides UDOT with useful tools that identify segments of concern along state roadways. The ISAM is used to analyze state route intersections to identify intersections of concern in the network, and the 2 together provide a complementary analysis of the state route crash data. UDOT uses these findings to prioritize the use of their safety funds. I'd like to finish up by thanking the UDOT project champions that I've had the privilege of working with over the years. As you can see, there are several of them, and I'm really hoping that I didn't forget anyone. I would also like to thank the many employees that I've interacted with in the research division. These individuals have been very helpful in all of the research that I've conducted, and I've appreciated all of the work that they put in helping our projects to move forward. Most importantly, though, I would like to thank the students. At the end of the day, although the research completed is very interesting and is beneficial to UDOT, the most important thing that is developed through the course of any research project is the knowledge and skills of the research assistants who work on these projects. I see these same individuals today leading in their companies and in various professional organizations. And I like to think that part of that is because of the work they did as a research assistant. The reality of it is, some of them like their research so much that they're now looking for their own research projects and are competition to me in obtaining research funding. I'm not sure I really thought about that as I was moving forward in this process. But on a serious note, thank you for the work that you have done. I could not have done any of this without your hard work and dedication. Thank you for helping me to be successful in my career. I hope that I was also helpful in helping you to be successful in your career. Thank you again for this great honor. I'm honored to receive it. And just in case anyone was wondering, I'm definitely not done yet. I look forward to many more years of UDOT research. Thank you.